Bonjour à tous. Hello everyone. Je vous souhaite la bienvenue au webinaire CeRVIM de ce matin. I welcome you to this morning's CeRVIM webinar. Et professeur Robert Bergevin va présenter le conférencier. I will ask Professor Robert Bergevin to present today's speaker.
Et merci Annette. Donc, mon nom c'est Robert Bergevin, je suis professeur au département de génie électrique, génie informatique. Et puis, Mohammad Baradaran, qui va faire le séminaire ce matin, est un étudiant que je conseille, que je dirige au doctorat depuis maintenant 2 années. Mohammad a fait ses études en Iran auparavant, bac et maîtrise, et puis a commencé son doctorat. Le sujet qui l'intéresse, c'est la détection de ce qu'on appelle les anomalies dans des vidéos. Donc, on a des vidéos, ce qui peut se passer, différents types d'actions, de choses qui se produisent. Puis, c'est très général comme problème. L'idée, c'est d'essayer de voir lorsqu'il se passe des choses qu'on ne connaît pas, qui sont imprévues. Donc, évidemment, pour arriver à déterminer quelque chose d'imprévu, il faut avoir des attentes, il faut connaître un peu ce qu'on s'attend de voir dans la vidéo. Donc, un processus d'apprentissage, d'entraînement pour savoir qu'est-ce qui serait normal de voir dans la vidéo. Puis à partir de ça, on va essayer de déterminer, Mohamed dans son projet, une façon de détecter les endroits dans des vidéos où il y a des anomalies, donc où on pourrait porter attention par la suite, pour essayer de comprendre qu'est-ce qui se passe, ou réagir suite après avoir déterminé qu'il y avait possiblement des anomalies. Donc, Mohammad va faire sa présentation en anglais, si j'ai bien compris, et puis il va y avoir par la suite un peu de temps là, pour poser des questions, si vous avez des questions que vous aimeriez poser à Mohammad sur son projet, puis tout ce qui touche à son projet. Donc, Mohammad, je te laisse la parole pour la présentation.
Merci beaucoup. So thank you very much for everyone for attending this presentation. In this presentation, I will have a comparative review on deep learning-based semi-supervised video anomaly detection methods. And we will add some of the results of the experiments we conducted in order to provide in our review paper. So I'll try to keep this presentation simple to be useful for everyone from different research fields. And in the introduction section, I will provide you a view to the problem containing the basic definitions. And I will argue that why we generally formulate this problem as a semi-supervised test. And in the experiment part, we categorize the existing state-of-the-art methods in the field into 3 subcategories as listed below. And we will try to introduce each of them, providing some of the experiments, focusing on the strong and weak points of each of the methods, and trying to find out where does the false positive and false negative normally rise from. So as you know, surveillance cameras are ubiquitous nowadays, and you can see them everywhere inside the airport, inside the public places such as banks, in the borders, in the highways. So they are generally everywhere. But there is a big challenge here. Although they provide us with good information in order to keep the safety, in order to record some of the other useful information, but there is a big challenge, and I want to indicate this challenge with an example. In the international airport of the Istanbul, which has been opened recently, although it is not 100% active, but even in this situation, there are more than 9,000 active cameras recording the scenes from different places. And this is really terrifying to imagine that who is going to analyze all of these resources of the visual information. So there is a need for intelligence system in order to analyze these contents, visual contents intelligently and automatically, and in order to find the events of the interest. So they regularly see some of the patterns that normally happen similarly most of the day. But the people sitting here are interested to find and to detect some of the events which are quite different, such as the illegal behaviors or dangerous situations. And this is the definition of the abnormal events in the video. So the video anomalies are the patterns. As it is video, they can be appearance or the motion that they do not conform to the majority of the patterns in the video. So inside the recorded video, we normally, and for the majority of the time, we see some of the patterns which are similar and they are repetitive, but we are interested to identify and detect the events that do not conform to the expected behavior. For example, if we just monitor the trajectories of the vehicles, all of them driving straight through the days, for example, thousands of the straight trajectories here, the one who has a U-turn here among these thousands of the trajectories is quite interested for the viewer of this surveillance camera, because it is most probably an illegal U-turn. And it is not because of just because of the motion pattern. They can be because of the appearance. And it's very interesting that the appearance itself has a variance in its definition. So as it is video, we are trying to focus on the appearance to see that if there is unseen appearance inside our videos and unseen object inside the video, we are trying to focus on the motion. And also we should consider the correspondence between the motion and appearance, because inside the scene, maybe we see some of the motions which is normal for some of the objects, but it is not acceptable for another object. So we should consider the correspondence between the motion and the appearance. And as a final note about the introduction, we have a very big challenges in video anomaly detection, because first, there is no limited and precise definition for the anomalies. For example, for a trajectory, it can be in any of the shape in order to define it as an anomaly. There is not a precise boundary between the anomalies and normals. Most importantly, these anomalies are rare. They happen rarely. So we don't have enough labeled anomalies for supervised anomaly detection. And this is maybe the most important and the challenging part, that anomalies are highly contextual. And the definition of the anomalies is variable for the scene from one context to another. For example, imagine for the same road, if it is a summer sunny day, a moving car at the speed of 100 kilometers per hour will be defined as a normal behavior. But if the same car moves here with the same speed, which is defined as the normal and allowed speed, it cannot be identified as normal anymore, because regarding the situation, it should be moved slowly. Or even the bears, they can be defined as anomalies here, but if they are out of these fences inside the jungle, they are a normal pattern. So as we said, we don't have enough label data for the anomalies. So we cannot define the task as a supervised formulation, although most of the tasks in supervised methods provide good results. Even it is not good to formulate them as an unsupervised task, because experiments show that they are not useful. But we can define them as a semi-supervised task, because not only we have enough data for the normals, but it is also compatible with the definition of the video anomaly detection, because we said that anomalies are the patterns which deviate from the normals. So how to formulate this task as a semi-supervised task? The researchers in the field benefit from one general rule in the training of the machine learning models or deep learning models. Imagine that you, in most of the applications, you train a model with a data set, and considering the validation results, when you want to evaluate your results on the same data set, you expect to get the same results because the data are similar. But if you test your model on an unsimilar data which have not been trained on, you cannot expect the same result. So we are going to use this general rule in order to define our video anomaly detection as an semi-supervised test. So the first categories in this field of the research formulate the video anomaly detection as an frame reconstruction. So they try to train a model, usually an autoencoder. And when we train an autoencoder with normal data, we expect the low reconstruction error for the same normal data. But we cannot expect the same reconstruction error. The reconstruction error will be comparatively high for the abnormal frames. So what they do, they train an autoencoder, they extract the reconstruction results, or white space of their regularity score. And for the frame that the regularity score is low, it shows that it is most probably an anomaly, and vice versa, it is normal. But there are so many different methods and researchers in this field, but there was not a big jump between different proposed methods. And we try to analyze what is the main problems come from and why they cannot make a big jump and considerable jumps for their performances. There were very simple errors. There were some very simple facts that they have not been considered in this formulation. First of all, it is the effect of the numbers of the objects in the frames, because most of these frames consider and analyze the frames entirely. So if the numbers of the objects is considerably variable between frames, it will make our method fail. And it shows that although this frame contains only normal frames, but it has a high reconstruction error that shows that it is an anomaly, but it is not. And also, this result also showed repeats the same things. This one shows an anomaly inside the frame, but this one doesn't show the same, this frame doesn't contain any anomaly, but their regularity score is somehow the same. It shows that there are some failures. The first one, as we said, the numbers of the objects matter. The second one, the distance of the objects of the interest from the camera matters a lot. And most importantly, these methods, as they try to reconstruct the frame, they focus on the low-level features. So they do not generally consider high-level features as a class of the objects. They mainly consider about the intensity or the color of the objects. We repeated the other experiments in order to validate same results, as we can see here. For a car, it just detects some parts that have generally different intensity in special places, because it is sensitive to the places, it is aware of the location. So if you want to conclude these methods, they don't learn about the class of the objects, they focus on the pixel intensities. They are very vulnerable to the number of the objects inside the frames. They do not consider the distance of the objects and the object size, and they can generalize to the anomalies. And even if we repeat the same experiment just on the motion patterns, for example, the optical throw or the difference of the frames, the same situation exists here. It is very, very sensitive to the numbers of the objects, so it is a problem in these categories. So some of the others, in order to help the system to consider the motion, they try to reconstruct the consecutive frames instead of the frame itself. But as the first convolution layer ruins the motion patterns, it is not effective in considering the motion. And the other previous challenges are still existing here. So these experiments show that the motion should be considered explicitly. So the other method provided by Yong Shin, they try to embed an temporal autoencoder inside the appearance autoencoder. So in order to consider the evolution of the frames, it was effective in considering the motions, because the result shows that if there is an abnormal motion, there is a big fall inside in our regularity score, but it is for some special cases. It is because it is not perfect in all of the situations. As talked before, mainly as it considers the frames entirely, it is very sensitive to the numbers of the objects inside the frame. So you can see here that the more objects we have inside the frame, the lower regularity score, although it doesn't contain any abnormality. It is one of the main problems that they show false positive in their results, and they cannot increase their performances. Even in this frame, although there is an abnormal object, but it is not considerable because it is in a far distance, and it is affected by other features such as appearance. So the same results also admits the previous conclusions. It is more sensitive to some places, the places near the camera. It is sensitive to the numbers of the objects inside the frame, and also these ones as well. So as a conclusion, although they try to benefit a temporal autoencoder, so they are aware of the motion, but although they are aware of the motion, appearance plays more important role than the motion. Our other experiments also admit that. We don't have any idea about the class of the object because we didn't give this information. They try to reconstruct the frame. They focus on the low-level features. Like other previous methods, it is very sensitive to the object size, and the distance of the objects from the camera matters a lot, and the background also affects the results considerably. So maybe another interesting method proposed in this field was trying to formulate the problem as a prediction task. So they try to provide a model with consecutive frames, and they ask the model to see these consecutive frames and they predict the next frame. So the model is implicitly trained in order to consider the evolution of the frames and in order to consider the motion patterns. But our experiment again shows that there is one problem. First, in one branch approaches, we will conclude it in the next slide, as the appearance dominates the motion features, they should be considered separately. So if you want to consider both the appearance and motion features in one branch in the same model, the motion features will undergo the appearance features. And also, again, as it considers the frames entirely, it is vulnerable to the numbers of the objects inside the frame. And also, as we have not provided the system with the class of the objects, it does not have any idea about the class of the objects inside the frame. So in order to validate one of the ideas, we tried to generate a synthetic big motion in one of the frames, so that this big motion is just for the normal objects. So in this frame, we don't have any abnormal appearance. If there is an abnormal motion, it is because of the normal object. But as you see, although it was a big motion, it was far faster than the other motions inside the clip. But the fall inside for the reconstruction error is not considerable in compared to other ones. So if we want to apply a threshold, it is most probably will be identified as a normal pattern. So we will miss this big motion because, as we said, appearance plays a more important fact. So as a final approach that we try to examine in our experiments, we try to re-implement the object-centered approaches. In this object-centered centric approaches, they propose to detect the objects of the interest, they crop it out of the frame, and they analyze it individually. So they analyze just the objects of the interest. They don't analyze the background or etc. And also in their paper, they propose to analyze the motion and the appearance in different branches. So it is very effective in order to consider the motion appearance, because we can see the differences in the pattern, in the motion patterns individually, not dominated by the appearance features. But there is one problem. Although we crop objects out of the frames, but we try, this method, it tries to reconstruct the same frame. So it is trying to use the frame reconstruction again for one branch. So although it focuses on the object, it is not aware about the class of the object. Like previous methods in frame reconstruction methods, they can be generalized on the anomalies. And there is another big problem for object-centric methods. We crop the objects out of the frame, so we lose the information about the location of the object inside the frame. In some of the data sets, the presence of one object in different places has a different effect on the results. For example, if there is a car inside the street, it is acceptable, but if it is in the watchways, it is not acceptable. So if we crop the objects and we analyze it individually, we lose that information. Just another experiment we add to our implementation in order to see that are these, because they focus on the objects, if this focusing on the objects helps them to consider the class of the objects, the frame reconstruction, although it is a cropped image, doesn't show any difference for the regularity score or the reconstruction error between the normal objects and abnormal objects. Although it is comparatively better than just considering the low-level features, but there is not any meaningful differences and it is not effective. But we also try to extract the high-level features for these normal pictures and abnormal features using a pre-trained VGG19, and we try to train an autoencoder in order to learn their high-level features. And we see that if they are trained on the high-level features, they can identify and discriminate between the normal objects and abnormal objects. So in order to conclude, we can see in all of these proposed methods in the state-of-the-art papers, although they have came up to very interesting formulations in order to solve the problem, but they simply forget to consider some of the simple points. And it is the main reason that they produce false negatives and false positives. We try to consider these experiment results in order to come up to a new idea. And also in order, we try to consider these shortcomings and solve them as much as we can, which I will try to present them in another presentation. So if you have any question, I'll be glad to help if I can. Thank you so much.
Merci beaucoup, Mohammad, pour ta présentation. Thank you, Mohammad, for your presentation. So if you have any questions, please feel free to ask your questions or to even write them in the chat if you prefer.
Hi, Mohammad. Thanks for your presentation. I have a question regarding the object-centric approaches that you talked about earlier. Yes, please. So let's say we have the object-centric approaches. What is your object of interest? How do you define? Sorry, how do you define it? And let's say we have CCTV cameras, and it's an occluded scene. So how do you define those, let's say, objects of interest, and how you would tackle the problem if there are far more than one object or whatever in the scene? Thank you.
Okay, thank you very much for your question. In fact, as I said, it's a contextual problem. So we define the impact and normal based on the context. So before the formulating the problem based on the different data sets we have any pre-knowledge about the data sets. For example, in the UCSD data set or the Shanghai data set, this is the Shanghai data set you see. So before the training the model and before evaluating it, we have any prior information, and we know that the objects of the interest are the people, just the people, for example, in these data sets. So they try to take advantage of some of the state-of-the-art object detection approaches, such as YOLO version 3 for this paper, although we have other versions, in order to identify the objects of the interest. In the test, in the evaluation time, again, they apply the same object detection approach, and they try to detect any of the objects inside the scene, and they try to feed it to the model to see that if the reconstruction error is similar to the normal patterns or not.
Thank you. One more thing. Let's say you first talk about the I think Istanbul airport.
Wait, Istanbul airport, exactly.
Let's take another airport, no matter where. So are they using any of these approaches real time in those airports? And which, just curiosity.
Exactly. I don't have any information if they are using any approach, but I just provided this information to show the importance of the intelligence system necessity for these public places. But I don't have any idea if they are benefiting any of the similar approaches for their places or not. Unfortunately, I don't have any idea about it.
Okay, thank you. Perfect. Thank you.
You're welcome. Thank you.
Would anybody else like to ask a question? Est-ce qu'on a d'autres questions? Si on n'a pas d'autres questions, je remercie beaucoup Mohammad Baradaran encore une fois pour sa présentation. Et vous pouvez aussi contacter Mohammad directement par courriel si vous souhaitez avoir plus d'informations sur son projet de recherche. So I would like to thank Mohammad Baradaran once again for his presentation. And if you have any additional questions, you can also contact him directly by email. So thank you very much, everyone, for your time today. And perhaps we will have some more webinars during the summer, or perhaps we will resume again in the beginning of the fall. Donc, ça, c'était notre dernier webinaire de cette session. Possiblement, il y aura une ou des webinaires pendant l'été. Sinon, on se reverra à l'automne. Merci.